the second video from Module 9, Cost at Neighborhood Level. In the previous part, we looked on how we proceed from building to neighborhood level and which parameters can represent the density at this neighborhood scale. In this second part, we will translate our real neighborhood to an abstract model, similar to what we did with the equivalent box building at building level. We will also look at the calculation tool that will be used to estimate the investment cost at neighborhood scale. Why will we make an abstract model of our complex neighborhoods? Because this enables to compare the various case studies, which would be very difficult if we keep it to the complexity as they are today or in reality. Moreover, we will graphically represent these abstract models so that we can more easily interpret and compare the cases. We will do this by translating our specific case to a fragment, so a neighborhood with rectangular plots and perpendicular streets, which typically is not the case in reality, or is not always the case in reality. The abstract model consists of 4 street rows. What I mean with street row is indicated here in the red box on the drawing. So one street row consists of several plots, and on each plot one building is foreseen. There are 4 streets. The streets are separated by roads. A road which is parallel to the width of the plot, and a street which is parallel to the depth of the plot. We will look for all of your cases. We will assume there are 4 of these streets, so it will be the same for all cases. The dimensions of the plot, so the plot size and the dimensions of the streets, will be determined based on your real cases. It might be that you have chosen a building which is not repetitive, which is a single building in a complex neighborhood. What you will do then is you will make an assumption and position this building in a repetitive neighborhood as is shown here. So you assume a number of buildings in a street, and the plot size should be more or less identical to your real plot size. You will assume the streets surrounding this building and translate them to rectangular streets. So the length of the street and the area of the real streets will be important to translate it in a correct way. It might also that you have a larger neighborhood than just 4 streets. Then you just take part of it. Then you don't consider the full neighborhood, but you just select a part of this neighborhood. So it means that you choose a part of your neighborhood which can be well represented by 4 streets and 2 roads, which is then repetitive again in your larger allotment. Now, typically in reality, it's often a neighborhood like this. So you have buildings scattered around, not following such rectangular grids, and you have roads which are also not perpendicular to each other. So what you do is based on the total area of your neighborhood and the amount of buildings, the square meter of buildings you have, you define plot sizes looking at an equivalent length and width which are representative for your real case. The same for the roads. So you choose 2 types of roads, a smaller one or a more narrow one and a more larger one, and then you calculate the length of the streets for the full area of the building to translate these to the simplified model. So we start from the box building, the equivalent box building from the previous module 8 on the building calculation, the cost calculation at building level, where we defined an equivalent box building. And we will put this box building, in a street. You need to define how many of these box buildings you have in one street. And we assume that each plot has identical sizes. So is rectangular and all have the same width and the same depth. So you can, if this is not the case in your real case study, you can calculate an average plot size. We will not look at one street, we will look at 4 streets in total, and we will therefore define 2 roads in this neighborhood. One road which is parallel to the width of the plot, so this street is parallel to the width of the plot. Then we have on the other side of the road we have a second row of buildings, and then we have a second street which is parallel to the depth of the plot. So this is the depth of the plot, and this street is parallel to it, which can have a different or the same dimensions of the other road. So it can be larger, more narrow, or the same width. And then on the other side of that road we have again the same pattern as we have of our first 2 rows of buildings. So this is a simplification we're going to make, which allows us to more easily compare the densities between the different cases and to have a good understanding of the differences in the cost related to these differences in densities. So to come back to the 3 buildings we looked at in module 8, where we calculated the cost at building level, we now put these box buildings in our abstract neighborhood model. So the first was a detached house with a floor plan of 10 by 10 meters. The second one was again a detached house, but now with a floor plan of 20 by 5 meters. And the third example was a terraced house with a facade width of 5 meters, and which was 10 meters deep and 3 stories high, so 10 meters high. For each of these, I assumed there are 5 buildings in a row with an average, plot size equal to the one, or on average the same as the one in reality. The streets are defined, and here I assume that the streets have the same width in the 2 directions. Again, we have 5 buildings in a row for the second part and 5 terraced houses in a row for the third example. For the graphical representation, in reality it could be that these terraced houses are bordering the streets. What you then do is, or the model will automatically, when we generate the drawing automatically in Excel, it will put it in the middle of the lot. However, the size of the unbuilt area, so the green part of the plot, is then here divided in 2. So if this would be a backyard, if you only have a backyard, then the full depth of the backyard is now divided into half of it is behind the building and half of it is in front of the building. But so in reality, it probably is all at the backyard. For example, if we look back at our buildings where we looked at a typical neighborhood in the Belgian context, this was a typical neighborhood consisting of single-family detached houses, where we see that for each of these the plot size is a bit different. But what we do is you calculate the full plot size and the full building areas, and then you make an average plot size for a certain building size, an average building size. Or what you can also do is you just take your building and you replace all the others by the same one here. That's the other alternative. And then you get this kind of simplification. You have a certain dwelling, your box building, in a street with a number of buildings representing reality. Then we have a street in that direction and a street in that direction, and then we mirror the street or the row of houses we mirror to that side and to the other side. And our simplified neighborhood model will look at this part of the full neighborhood scale. This leads us to the second part of this video, the cost calculation tool that we will use to estimate the investment cost of buildings, including the cost for the land that we need, but also for the infrastructure that we need to serve and access our buildings. This picture shows you the total input that we need for the neighborhood calculation. The first part is here hidden because it's the part that you already inventory, that you already input at building level. Now we have 5 additional inputs that you need to provide in the Excel file to calculate all the other parameters. Namely, for the simplified model, you need to enter a width of the plot and the area of the plot. You need to define how many buildings you have for one row, and you need to define the width of the two streets. The width of the street parallel to the width of the plots, and the width of the street parallel to the depth of the plots. For each of these, you define the width in meters. Based on these additional inputs, a variety of additional parameters will be calculated automatically, but you will calculate it first manually to ensure that you understand what is being calculated in the Excel file. The different parameters that are calculated are parameters that represent the density of the building and will then be used later on also to calculate the various ratios needed to calculate the cost at neighborhood scale, but that's in the next session. So let's have a look at these different parameters to be calculated step by step. The first set of parameters relate to the building plot itself. So we first look at the building plot, and what you need to input it is the width of the plot and the area of the plot. And these you define based on your real case. Once you have defined these two parameters, the depth you can calculate by dividing the area by the width of the plot. So with the two parameters, you have the 3 values you need. Then we go from the building plot to the fragment. So now we looked at one building plot. Now we will go to the fragment. Well, the fragment, we first of all need to define the total length and the total depth of the fragment, so the total size of the fragment. When I talk about a fragment, it means the 4 rows, so the 4 rows of buildings. So we have, this is the total fragment we are looking at. So it's the 4 streets and the 2 roads. If I want to define the width of the fragment, well, I don't need any additional input. You can calculate it from the width of the plot that you already have defined. You multiply that by the number of buildings in one row. You multiply it by 2 because you have 2 sets of these buildings, and you add the width of the street that is parallel to the depth of your plots. By doing that, you calculated the full length of the full width or the full length of your fragment. To calculate the depth of the fragment, you need to add up 3 parts. First of all, you have the depth of the plot, one plot. You add the width of the street that is parallel to the width of your plot, and you add again the width of a plot. So 2 times the depth of a plot, 2 times the depth of the plot, and you add the width of the street. So by that we have the full size, we know the full size of our plot, both the width and the depth of the plot. Then we go to the next part, we go to the streets. And once we know the street area, we can calculate the residential area and the total area of our fragment. So, looking back at our fragment, first we define the area of the street. Again, we can calculate. We don't need any additional inputs besides the width of the street, but that has already been input before. So how do we calculate the area of the streets? Well, first of all, we make an agreement. So there is a tricky part that we could double count the crossing of the streets. So therefore, we assume that the street parallel to the width of the plots is this part and this part, but not the crossing part. So that section we don't count for the area of the street parallel to the width. We add this crossing section to the area of this street, not to count it twice. Once this is defined, we can first of all calculate the area of the streets which is parallel to the width of the plots. This is the width of the plot multiplied with the number of buildings for one row. Then we have this length, and we multiply it by 2. Then we have also the length at the other side. And that length we multiply with the width of the street, and so we calculated the area of that street. For the area of the street, which is parallel to the depth of the plot, we first of all calculate the depth of one plot. We multiply it by 2, then we have the two sides, and we add the width of that street, which is parallel to the width of a plot. By adding all these, we calculate the total length of the street parallel to the depth of our plots, and that we multiply to calculate the area. We need to multiply it with the width of the street. The lengths of the street are easy. It's just the first part of the two terms. So this part and this part without multiplying it with the width, then you get the length of the streets. So with that, you can calculate these four numbers. The residential area is defined as all the areas of the full fragment without the street area, so without the road area. So it is actually the area of all the plots. So the area of one plot multiplied by 4 or 5 or 6, I mean with the number of buildings in one row. Then you have the residential area of one row, and that you need to multiply by 4 because we look in our fragment to 4 of these rows. The total area is then the residential area plus the area of the street parallel to the width of my plot plus the area of the street which is parallel to the depth of my plot. With these calculations, we can also translate the total area which we have calculated in square meters to an area in hectare by dividing by 10,000. A last input that we need to calculate before we can look at the density parameters is the difference between the built-up area and the total floor area. The built-up area is the footprint. So it's really the ground floor area of all the buildings in our fragment. While the total floor area are the floor areas of all the buildings, but looking at the different floors in a building. So if you have a building with 4 floors, you need to add up the total floor area of all these floors. So the total floor area at neighborhood level is the total floor area of one building multiplied with the number or by the number of buildings per row and by 4 because we have 4 rows. And the built-up area is then the total floor area divided by the number of floors per building because these are the same for all the buildings in our fragment. This means if I look at my numbers, I have a built-up area in my example of 1,200 square meters, which is the physical footprint of all my buildings in my fragment, and I have a total floor area of 2,400, which means that I have 2 floors in my buildings, the ground floor and level 1. Now we have calculated all the parameters to calculate the density indicators. The first indicator is the circulation density. We look also at the residential density and the built-up area. Let's have a look at these. The circulation density is here defined as the circulation divided area divided by the total area. So it's a dimensionless number and we put it in a percentage, so we multiply by 100. How do we calculate it? Well, the circulation area, it's actually the full street area. So it's the 1,200 plus 1,000 square meter. Or it's the total area, 7,000 minus 4,800, which is the sum of all the plots, the area of all the plots. And that we divide by the total area. So these two numbers, with these two numbers you can define the circulation ratio to the total area of the full fragment. The second density indicator is the residential density. It is the residential area, which we have calculated before, so the area of all the plots divided by the total area of the fragment. And in this case, it equals to 69%. Because the sum of these two should be 100%, of course. You have the circulation part and you have the non-circulation part, or the residential part. A last density indicator is the built-up area compared to the residential area. So it's mean the red part of the build-ups. So if I go back to my picture, it's this part, so all the areas of the buildings, but only the ground floor, compared to the green area, which is the residential area. So all the plots, the sum of all the plots is the residential area. And I now want to know from this residential area, not looking at the roads, how much has been built upon. So what is the footprint of my built environment on these residential areas? And that is what is calculated in this third term. So I can calculate it by dividing the built-up area through the residential area. And in this specific case, it's 25%, or 1/4 of the residential area has been built upon. The last two are the circulation density and the net population density. The circulation density is here expressed in the length of the roads in meter divided by the full fragment area in hectares. So the length of the roads is already defined before. It's the 170 meter in my case, divided by the 0.7 hectares. So it's the length of the two streets divided by the total fragment area. The net population density cannot yet be calculated without one further assumption. Namely, we need to know how many square meters of floor area we have for one person. Well, we will assume for all of you that we need 10 square meters of floor per inhabitant, which is for some quite small, for others an average, and for other contexts very, very high. So the 10 square meters per floor is just to compare the different cases. For Belgium, it's very low. In Belgium, we typically have for 4 persons a house of 120, 160 square meters. So we have 40 square meters per floor. So this is quite a low number for the Belgian context, but not for others. We just put this as an assumption. If you want to change it later on to make additional assessments, you are free to do so. But for comparative purposes, we will first look at this, assume the same density for all of you. 10 square meters floor per inhabitant is equal to 0.1 inhabitants per square meter floor. And with that, of course, we can calculate the net population density. It is the total floor area multiplied with the area per inhabitant, multiplied by the number of inhabitants per square meter floor, and we divide that by the total fragment area. So it's 2,400 multiplied by 0.1 and then divided by 0.7. And so you calculate the net population density, which is also shown here at the bottom of the slide. That's the final calculation to be done. Based on all of these, we will first of all graphically represent the density results. More specifically, we will graphically represent the population density, the circulation density, the residential part that is open, the residential part that is built up, and the circulation. So the sum of all of these is 100%. So the circulation plus percentage plus these is 100%. That's the circulation, that's the other part. And from that part, from the residential part, we look at the part that is built up, so where we have a building, and which part is the garden, the backyard of the building, which is open, so the gardens, let's say. We will present it in such way. So we will, first of all, the population density will be shown by dots. So you calculate the density, you divide it by 20, because we assume that one dot represents 20 inhabitants per hectare. And by dividing the calculated density of your neighborhood by 20, you can calculate the number of dots that you need to draw. For the circulation density, you first can calculate the density of your specific case. So, for example, 238 meters of roads per hectare. And then one line, the length of such line is 25 meters. So by dividing this number by 25, you know how many of these lines you need to draw in this quadrant. And you equally distribute the number of lines. And finally, you make a bar chart where you calculate the circulation density, the residential part that is open, so the green area, which was also indicated in green on the different figures in this presentation, and then the residential part that has been built up, which is not the total floor area, it's only the ground floor area. And with this, I will end this presentation. The next presentation will focus on the prices and makes the step together with the ratio calculations to the full cost estimation at the neighborhood scale.